Anything that moves has momentum. Anyone working with moving objects or fluids must be aware of that momentum if they're to maintain control. Momentum is an important principle to consider because so much of our technology moves. It takes the force of an impulse to get something moving, and once it is moving, momentum will try to keep it going. Momentum can work for you when you want to keep something moving, and it can work against you when you want something to stop. This entire rollover is happening because of the momentum of the vehicle. If you want to stop an object in a controlled way,
Do you see that moron? I got 59,000 pounds on and he thinks I can stop on a dime.
it's important to know how much momentum the object or the fluid has. Momentum depends on the mass of an object and its velocity. If you don't have a lot of mass, you can still develop momentum by moving very quickly. On the other hand, the more massive an object is, the more momentum it has. There's simply more of it to stop. These are the two considerations in momentum, mass and velocity. The same principles hold true in rotating systems. The amount of momentum depends on how fast the object turns, or its angular velocity, and its moment of inertia, which acts like mass in a rotating system. But there's another side to this story, which is the relationship of momentum to force. When a moving object hits something, it exerts a force. The amount of force it exerts depends on the amount of momentum the object has. If there's a lot of momentum, there will be a lot of force when the time is short. This is the impulse, a force acting over a period of time. Fortunately, you can change the amount of force in an impulse by changing the period of time over which it acts. This is the principle behind shock absorption and what the plumber did with the air trap. The air acts as a shock absorber, letting the water stop over a longer period. The time was increased and it decreased the force of the impulse. Impulse is also what gives an object or fluid momentum in the first place. The engines of a plane apply force for a period of time long enough to accelerate the plane up to flying speed. But on an aircraft carrier where space is limited, the planes have to reach the same flying speed in a much shorter time. This takes more force, so a catapult is needed to provide the extra pull. These are the two elements of a moving object. Its momentum, which depends on mass and velocity, and the impulse, a force acting over time that either gets the object moving or is produced whenever the momentum changes. Once you know this relationship between force, time, mass, and velocity, you can calculate the amount of momentum in a moving object or fluid, and you can control how that momentum becomes an impulse when the object or fluid changes its momentum. Anything that moves obeys this relationship between impulse and momentum. We've also seen how the amount of momentum you start out with is always the same as the amount you end up with if the system is isolated. That means that if you change one element of an equation, another element will change to compensate. This vehicle's momentum is being absorbed over a long period of time. If the time of the impulse is shortened, the force of the impulse increases because the amount of momentum has not changed. This conservation of momentum is especially important in rotating systems because the moment of inertia can change if an object changes shape. For Bob Muckle, this conservation of momentum affects how his spinning satellite behaves in space.
This is a very massive spacecraft and has a great deal of angular momentum stored in it. Late in the mission, we have a situation where angular momentum is conserved, but the spin rate changes a great deal. And this is caused by extending some wire booms out of these black boxes that are located on the spacecraft. These booms actually only weigh a few pounds each, but they're extended 50 meters, rather like this ruler. They continues out, and this tape rule is very light. The moment of inertia that it contains by the time you extend it 50 meters is very great. And the effect of this is that by the time these booms are out 50 meters, the spin rate of the spacecraft is decreased by a factor of 2, simply due to the fact that the moment of inertia of the spacecraft is increased so much.
Knowing about momentum and its relationship to force enables technicians and operators to predict and control technology in motion. By the way, have you figured out why the wheels of an aircraft are not spun up to speed just before landing? The wheels are very massive, and if set spinning, would have a lot of angular momentum. The landing speed of a plane varies because of winds, so it's hard to match the speed of the wheels to the ground. If the wheels were spinning too fast, their angular momentum would become an impulse that would speed the plane up. A pilot is more interested in slowing down. This program was produced under the direction of AIT at the facilities of Telemation Productions and is part of Principles of Technology, a project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development. Together, serving education.